Hey folks, so my name is Stephen Slaughter, and thank you for joining us at the USGS Landslide Hazards Seminar. This meeting is hosted by the Landslide Hazards Program and co-organized with contributions from Matt Thomas and Jamie Kostelnick. For those of you who are new to this meeting, you have the ability to submit questions via the chat window or to use the raise your hand feature in combination with your microphone and video camera. We'll wait until the end of the presentation to take questions. In the meantime, please mute your microphone when you aren't intending to speak. So today it's my pleasure to introduce Alex Strauff. Alex is a consulting engineer at BGC Engineering in Golden, Colorado, and a PhD candidate at the University of British Columbia. He has spent much of the last 2 decades assessing landslide hazards, assessing or quantifying risk, and designing debris flow mitigation structures for local governments and infrastructure owners. Beyond working hours, you will find Alex somewhere outside, usually with his 2 kids. Welcome, Alex. The time is yours.
Thank you, Stephen. As Stephen mentioned, I'm working on my PhD, and that's following from much of my consulting work. And what I hope to share today is mostly written in my PhD thesis, which will come out later this spring, and you'll be able to find it at the UBC library online. But my thesis is a compilation of papers that are already published, and I'll provide references at the end of the presentation. Or, of course, feel free to email me. I look forward to speaking with you. Most of what I will share today is based on experience working in British Columbia, Canada. British Columbia is a mountainous place, and because of that, there are many landslides. And the infrastructure and homes tend to be located on the valley bottom, in between the floodplains and the steep slopes. And for the past 20 years or so in British Columbia, we've been using quantitative risk assessment to help us make decisions when there's landslides interacting with infrastructure and people. And this is what I will talk about today. The main message of this talk, and what I want to leave you with, is that quantitative risk assessment can be a very useful tool for supporting decisions, but quantitative risk assessment can also be very complicated and sometimes counterproductive. And the presentation, I hope to share some tips for how you can do quantitative risk assessment better. Today's talk will be in 2 parts. The first is just an introduction to the topic of quantitative risk assessment. And the second half will be a summary of key lessons that we've learned. My colleagues and I have been doing risk assessments for a long time, and it's been a very humbling process. We've made a lot of mistakes, and I'm hoping that with a few of these lessons, we can save you from some of the mistakes that we've made. The story of quantitative risk assessment began in British Columbia in January of 2005. Late at night, one night, a woman was asleep in her home when a landslide came and crushed the home and killed her while she slept. And most concerning to the local government and to the people working in that area was that the characteristics of that particular slope and that specific landslide did not appear to be unique. There was this 80 to 100 meter high escarpment and glacial marine silts and sands that extended for more than a kilometer, with houses right at the toe of the slope as well as houses right at the slope crest. And the local government needed to decide if those other homes were safe enough from landslides, or if they needed to be evacuated, or if something needed to be done to stabilize the escarpment. Landslide specialists in Western Canada at that time were people like Aldrich Hunger, Nordy Morgenstern, and others. They had experience working in the dam safety industry and also on landslide hazards in Hong Kong. And in both of those places, there had been an effort to define safe enough based on the risk of death. And so what I'm showing in this slide at the bottom here, this is just a scale of risk. On the far right is a risk of 1 in 1, meaning that there would be certain death. And on the far left is a risk of 1 in a million, which would be pretty safe. And so they decided to set a threshold of 1 in 10,000. If risk was less than 1 in 10,000 per year of dying in a landslide, then the home was considered to be safe enough. And if the risk was greater than 1 in 10,000, then it was thought to be too risky, meaning that the home needed to be evacuated or the landslide needed to be mitigated. This 1 in 10,000 risk tolerance level came from the information that I'm showing on this slide. So the x-axis of this figure is age, a person's age, and on the y-axis is risk of death in a given year. This suite of curves here at the top is just showing risk of death in different countries for different ages of people. You'll see here where there's this low spot. This is for children ages 5 to 9. This is when a person is at their minimum risk of dying, and that risk is about 1 in 10,000. So that means that of children ages 5 to 9, about 1 in 10,000 of those children die each year from various causes. If you look at my age, I'm in this 40 to 44 year category. My risk of death is somewhere here above 1 in 1,000, meaning that about more than 1 in 1,000 people my age die each year from various causes. So the 1 in 10,000 threshold for landslides was set so that the landslide risk was less than this background risk of deaths from various causes for children, but it also happens to be similar to the risk of dying in a car accident and is something like 10 times higher than the risk of drowning. And so the goal was to reduce risk to below this background risk of death from various causes. So that was a discussion about the risk tolerance, the 1 in 10,000. Now I'll just briefly describe how we estimate risk. And I'm going to use an example. There's many other examples I could choose, but this example is for a landslide or let's say a debris flow impacting a home that's located on a debris flow fan. And the way that we would calculate risk, turn it into a number, is we would take these 4 parameters and multiply them together. The first parameter is the hazard probability. So you could say this is the likelihood in a given year that a large debris flow occurs. S is the spatial probability. So this would be, let's say for a given house, the likelihood that if the landslide occurs, this is the likelihood that it actually travels and runs out far enough to impact the house. T is the temporal probability, and this is the probability that a person is home at the time when the house is impacted. And then V, the vulnerability, is given that the person is home and the home is impacted, this is a likelihood that they are killed. Now, applying some numbers to these parameters, you could say at a given site that the risk of the the probability of the landslide occurring is about 1 in 500. You could assume or estimate using runout modeling that the spatial probability of impact is 50%. There's a 50% chance that this particular house is hit based on its location. That you could assume that the person is at home, say 80% of the year. This is a person that spends a lot of time at their home. And you could assume that if the home is impacted, there's a 50% chance that the person is killed. And if you multiply these values together, you would find an overall risk of 1 in 2,500 risk of death for that person in a year. And when you plot that on this risk scale, that's this red arrow here, you would see that that 1 in 2,500 is greater than the threshold, and that would tell you that you should do something to mitigate the landslide or to evacuate the home. So that example that I just gave is one very simplistic illustration of how we've used quantitative risk assessment. But in our practice, we use quantitative risk assessment for many different types of decisions related to landslides. And the reason we use quantitative values, and by that I just mean numbers, the reason we use numbers to describe risk instead of low, medium, high, is because the numbers help us make decisions. And I'm just going to run through very quickly a few of the other types of decisions that we try to make using quantitative risk assessments. One type of decision is related to sizing of landslide mitigation. For example, in this case, the example that I've chosen is we need to decide how tall should this particular debris flow barrier be. If we make the debris flow barrier too short, then a large debris flow could overtop it, and this could contribute to intolerable risk to the community downstream. Or if the barrier is too high, it just becomes too expensive to build. So we needed a method to justify the height of the barrier that we proposed. And we used a graph like this to justify our selection of the barrier height. And what this is showing is on the y-axis, this is just a measure of risk. So this is the life loss in 100 years, or the expected life loss in 100 years. On the x-axis is the size of debris flows that could occur. And we were able to estimate the risk associated with these different size debris flows. That's what the dots are on the curve. And we found that the smallest debris flow, this 0.2 million cubic meter debris flow, the risk of it is quite low because the debris flow is very likely to stay within the channel and not cause life loss. On the other end of the spectrum, on the right here, the largest debris flows, well, these would have a very high consequence, potentially killing more than 100 people, but the probability of this debris flow occurring is so low that the risk is also tolerable. And that led us to focus our design on this middle part of the curve, and we sized the height of the barrier to capture this 2.8 million cubic meter debris flow, because this is the largest event that was over into the intolerable risk zone. And then we allowed, with our barrier, we have this opening where we allow these smallest debris flows to pass through, which helps us to reduce our maintenance and debris cleanout cost. So now a second common type of decision that we use quantitative risk for is to compare between options for controlling landslide risk. This is an example where we were trying to decide between whether we should use guardrails or slope mesh to deal with the rockfall risk at this site. And this is a site with quite a lot of loose rock above the road and a steep slope below. And this is a fairly low volume road with little traffic. Now, of course, we can estimate the cost for the two options that we had, but the risk assessment allows us to also quantify the benefits. So in this case, we were quantifying the risk reduction that was associated with the measure. And the risk reduction just came from, we could estimate the risk without the guardrail in place, and we would estimate the risk with the guardrail in place in terms of, and then when you subtract those two, you find what the lives saved is by implementing the measure. And then if you just take the cost and divide it by the lives saved, you get a measure of the cost effectiveness of these two things. And so for this case, we could find that guardrails cost about $1 million per life saved, and the slope mesh $4 million per life saved. And that became a pretty compelling argument for choosing the guardrails instead of the slope mesh. And again, the guardrails were effective mostly because this is a low volume road, and the way people were being killed from the rockfall was by driving off the road if they intersected a rock that had already fallen. A third category of decision is related to if a place is safe enough or not, and whether it should be evacuated or closed. So in this case, imagine there's a park owner who operates a trail below a steep cliff with a history of rockfall, and they need to decide, if they keep the trail open or if they close it. Of course, if they close the trail, this could eliminate the risk, but how would we all feel if all the trails in our parks were closed because of small risks? And what I want to show here is really that you don't have to use a threshold of 1 in 10,000 to make this decision. You can use other things. So this is an example from New Zealand where they've taken their trails and they've classified them by category. So they've called a trail a medium risk trail, and if they classify it as medium risk, that would mean to the user that they should expect the risk on that trail to be something like the risk they face when they go swimming or biking or boating. So the user should recognize that accidents happen, but generally it's a fairly reasonable and safe place to be. And if the risk was much higher than that, they might classify it as a high risk trail and advertise to users that, the risk here is high, it's a dangerous trail, and if you come here, you might be facing a risk that's similar to whitewater rafting or rock climbing, for example. I know that was a very quick summary of quantitative risk assessment, but I hope it just gave you a sense of why we would want to quantify landslide risk and how it can help us make decisions. And the key message from all of that is that numbers help us make decisions, and that's why we quantify risks. But these quantities, these numbers that we assign to risk, they come from models of risk, and like all models, these numbers are wrong. Sometimes they can be useful, and this next part of the presentation is intended to help you make useful risk models and develop numbers that you can actually use. So I'll transition now to the second part of the presentation, which is on the lessons learned related to quantifying risks and making risky decisions. And I'll be sharing really the mistakes that I've been making over my whole career and hopefully try to keep you from making the same mistakes. It's been a challenge, but I've tried to combine and condense these things that we've learned into 6 key lessons, and I'll go through them one by one. The first lesson I call identify the decision. So the first step of every risk assessment and every problem really is to precisely identify the decision that needs to be made. And then the risk assessment that you use to help address that decision, it needs to be specific to that decision. So after a landslide occurs, or if there's an emergency, there's very often a rush to get involved into the project. And I think our natural pattern, mine certainly is to fall into the things that I am comfortable with. And those can be things like mapping landslides, or in my case, estimating life loss risks. And at the beginning of each project, we've started to realize that we need to give ourselves space and time to figure out what to get our bearings and to figure out the direction that we want to head in. So it's easy to arrive and feel lost in the forest, and it's very valuable to go slow and really chart our course rather than charge off in the wrong direction. So I'll give you 2 examples of this. The first case study is one that I'll return to several times in the next 20 minutes or so. And this is an example of me really solving the wrong problem and not recognizing the decision that needed to be made for many years, actually. And this was a project in Guatemala City. Guatemala City is located on flat land at the top of a plateau, and there are steep ravines that incise into this plateau. All of the flat land has been developed, and so people that are moving to Guatemala City, it's a rapidly growing city, and that's because people move there from rural areas where they're facing violence and food insecurity. They move to Guatemala City for economic opportunity, and then the only place left to live near the city is on these steep landslide-prone slopes. The government has declared these slopes to be uninhabitable due to the landslide hazard, but the people who live there, they recognize the landslide hazard and they tolerate it. And they tolerate it because the landslide risk is perceived to be much lower than the risk of violence and food insecurity that they faced prior to coming to Guatemala City. So when I first got involved here 10 years ago or so, my first instinct, because I'm a landslide person, was to map the landslides. So we went around mapping landslides affecting communities. And with time, we realized that this mapping of small-scale landslides, it doesn't help anything, because the community members are all readily aware of the landslides, and they're very comfortable with the language of risk, actually, and much more comfortable with risk language than any other community I've ever met in North America. Similarly, we were initially debating risk tolerance thresholds with the government, but that didn't really help anything either, because the government doesn't have much influence on what is happening in these areas. And so with time, we learned that the decision that actually needed to be made was something like, what is the most effective way to reduce landslide risk given all of the constraints, like a limited budget and limited technology options. So I think if I did this project now, I would have been much quicker to recognize the decision that could be made and where we could be effective. The second case study I'll show here is an example where I understood the decision to be made, but I went charging off on the wrong path of a risk assessment. So this is a case where we have debris floods. So there was a storm that caused debris floods in a whole series of catchments. And we came and did life loss risk assessments at a series of hazard sites because we wanted to use them to help us justify the sizing of mitigation measures that we proposed. And we had done this on previous projects successfully, so we thought that was the way to do it, is base our decisions on life loss risk. But after we finished the work, we realized that we could have very quickly recognized that the life loss risk was probably negligible or tolerable, and we should have focused our efforts on quantifying things like the indirect economic losses, because those indirect losses would have been much more helpful for us in establishing benefit cost relationships that would help us to justify our mitigation selection. So in conclusion, at the start of a project, slow down, figure out the decision that you are actually needing to make, and then set a work plan to support that specific decision. Now we'll move on to the second of the 6 lessons. And this lesson is that risk evaluation is complex. And when I say risk evaluation, I mean that point at which we compare all of the information that we have to make a decision. So early in my career, I had this impression that it was a pretty simple comparison of the risk estimate and some risk tolerance threshold. And that's what I showed you at the beginning. But I've learned more and more that it's usually not this simple. And I want to share with you a different framework for risk evaluations that might help you to lay out your projects and explain what influenced your landslide decision. So in your mind, travel back to the fall of 2020. And this is a time when the COVID lockdown had eased, but you were surrounded by fear of COVID and social distancing measures. And there was a decision that you had to make every day. You made the decision of what COVID protection should I wear? Should I wear a cloth mask or a hat or an N95 mask or something like this hazmat suit? And I think all of us would answer this question as, well, it depends. It depends on a lot of things. I can't just answer which protection would I wear without thinking through a whole series of factors. And I'd like to propose that the different factors that you are balancing as you decide what COVID protection to wear fall into these 3 general categories. One category shown here at the top is the risk estimate. So one thing that affects what protection you wear is how high or low is the risk. Another category is risk tolerance. So this is how do you perceive the risk and how important is the risk and what benefits do you get from taking the risk? All fall in this risk tolerance bucket. And then the third category here are the risk controls. And this is like, what are the things that are available to you to help reduce the risk? And the risk evaluation is this process of weighing information in these 3 categories and trying to find a reasonable balance that supports your decision. So for example, with this question, what COVID protection should I wear? These factors that are related to the size of the risk were things like, how old am I? If I'm 80 years old, I might wear a different level of protection than if I'm 20 years old. Similar for if you were immunocompromised. The third one here is, will I be visiting a COVID ward? So if I was a nurse visiting a place where people have COVID, I would have a much higher risk of contracting the disease than if, for example, I was in a park. And if I was going to a park in the open air, I might be happy to wear the cloth mask, whereas if I'm a nurse, I'm probably going to wear this hazmat suit. So those are the things that are related to the size of the risk. The next category would be things related to the risk tolerance. So I like to play soccer, and I learned very quickly that I can't play soccer in an N95 mask. I never tried to play in the full hazmat suit. So I started tolerating a higher level of risk, and I played soccer even without a mask. And that led to me contracting COVID and giving it to my whole family. But it was a decision that I made related to risk tolerance. Also, I can imagine that if I had had a close friend who had recently died of COVID, I probably would not have made that decision to not wear a mask while playing soccer. So the third category is related to the risk controls. So the decision of what protection should I wear was probably related in some way to whether or not I had already received the vaccine. So this very simple risk evaluation that I showed in the introduction, where I just take the risk level at a home and compare it to a threshold, yeah, there's a few places where this applies, but I don't want you to leave the presentation thinking that this is risk evaluation. This really only applies in a few situations, and it's not really a great general framework because there's so many decisions for which it does not apply. Instead, risk evaluations are complex. They require you to balance many different pieces of information. I don't intend to walk through this flow chart. I don't really mean for you to be trying to read it right now. I just want you to be aware that this exists, and it's structured around these three different categories. And the intent is that you could use it to help you lay out your project and help you lay out the different pieces of information that you balance in when you make a decision. The third lesson learned is that given that these risk evaluations are complex and that you're trying to balance many different types of information, all of the information is uncertain and incomplete, it's important that you use numbers that people intuitively understand, because if you're not using those intuitive numbers, it just makes the complex risk evaluation that much harder. So I'm going to prove this to you with a pop quiz. So this pop quiz uses number formats that I've used for almost my whole career until the last couple of years to communicate risk values. So let's imagine you have a landslide risk, a source of a landslide that has a risk of 1 in 10,000. And then let's imagine you have another landslide risk source that adds another risk that's 1 times 10 to the minus 4. And then you have some sort of mitigation in place that reduces it by 3e minus 5. So what's the risk level? How much risk are you left with? I'll take a drink while you work on that. So I know there's a handful of you that did this very quickly in your head, and you can just tell me what the answer is. But I'll assume that most of you, like me, probably didn't try to answer it because you know that I'm just trying to make a point here. And the point that I'm trying to make is that these numbers are hard to work with. Even for those of us who work with them all the time, they're not intuitive. So I'll take you then to the next version of this quiz, and I'll say that these are the same numbers. They're just translated into a different notation. And so here we have a landslide that has a risk of 100. There's a second landslide source that gives us another risk of 100. And then we have some mitigation that reduces that risk by 30. And we all know right away that our remaining landslide risk is 170. And I just want to make the point that if you use simple numbers like this, suddenly people can understand the relative impact of your different risk sources and your mitigation. So the units that we're using for this second version of the pop quiz is a unit for risk called micromorts. So a micromort is a 1 in a million risk of death. You simply take the risk value that you have, usually it's a probability, and you multiply it by 1 million. This translates that risk value usually to a number that's in the range of between 1 and a few thousand. And this means that now the number is a number that everyone intuitively understands. This was started in the medical field to compare risks related to different medical procedures. And now we're starting to use it for landslide life loss risk. And we use it because it helps us to identify errors in spreadsheets. it helps us understand the relative importance of the risk value versus our uncertainties, and it really helps us to describe risk to other people. One fact that I also find really helpful is that 1 micromort turns out to be similar to the daily risk of death for a person in North America for any type of accident. So, you know, we walk around, we could have a building fall on us, we could get in a car accident, and then if you take all of those types of accidents and put them together, there's a 1 micromort risk of death per day for each of us. Now, when we use these micromorts values, it really helps us put landslide risks into context. And I'll show that to you here. I'll walk you through this table. So we have 2 pairs of people. It's a mother-daughter pair. There's one pair who lives very close to the landslide at high landslide risk, and another pair that lives farther from the landslide in the distal runout zone with low landslide risk. So the adults, those are the red lines. The adults each have a background risk of death of about 2,000 micromorts. That's just based on their age. They're both about 40 years old. And the children, who are about, say, 5 to 9 years old, have a background risk of death of 100 micromorts. That's from all different causes. Now, the pair that live close to the landslide zone, they might have a very high landslide risk of 900. And it becomes, you know, quite obvious to see that the landslide risk is significant compared to the background. So for the child, you know, we're increasing the risk by an order of magnitude from 100 to 1,000. So the landslide risk is very significant for that child. And even for the adult, it's increasing their risk by, you know, almost 50%. Whereas for this pair who live in the distal portion of the landslide runout zone, you know, their landslide risk might be something like 10. And this is relatively insignificant compared to the background risk levels. Now I'll show you on the next slide. This is that exact same information, but just using standard notation, and those relationships just, at least they don't jump out to me. So I've stopped using this notation. Okay, now I'll move on to the final 3 lessons for risk evaluation. And these are based on the 3 parts, or those 3 categories that we try to balance in our risk evaluation. This lesson 4 is related to the size of the risk itself. And then 5 and 6 will be related to the risk evaluation and the risk controls. So this is related to the size of the risk and how we estimate that size. So the point I want to make here is that landslide risk estimates are always going to be uncertain. After you make a few of them, you realize how small changes in the inputs can have a really large effect on the risk estimate value, which then in turn has a large effect on the risk decision. So it's important to explore and describe the uncertainties, but regardless, you should probably have in mind that you don't really know the risk to any more of a precision than an order of magnitude. So if the risk you're dealing with is a snake, you could say you really just want to know, is the snake some small garter snake that wraps on your finger, or is it a giant man-eating snake, or is it something in between? And if it's something in between, there's usually not much point in debating if the snake is, you know, exactly 7 inches long or exactly 9 inches long. So now back to this point of using a best estimate. It's important that you don't intentionally overestimate risk. And the way that risks are overestimated is when you apply conservatism. And this happens very easily because many of us who are doing risk estimates are trained as engineers. And as engineers, you know, our whole career, we apply factors of safety to our calculations, and we choose conservative design parameters. And we do that because we want our designs to be safe. But a risk assessment is not a design. A risk assessment, or the risk estimate, is something that we're trying to balance against our risk tolerance and the controls that are available. And if we apply conservatism, it just skews that balance. So for example, if you have an actual risk, you know, the risk comes from these multiplication of these parameters H, S, T, and V. And if you have an actual value for your spatial impact probability of 10%, and you just shrug your shoulders and say, well, I'm not sure, let's just assume it's 1. And then same for the temporal, we don't really know, so let's assume it's 1. And the same for the vulnerability, let's just assume it's 1. You know, you could take a risk that's something like 5 micromorts, say like this little snake that wraps around your finger, and and treat it as if it's some giant man-eating hazard when it's not. And that's not helpful to the decisions you're trying to make. Similarly, you don't want to underestimate the risk. And the way that I see risk estimates being underestimated is by ignoring these low frequency, high consequence type of events. So here is two examples. On the left, you have a rock fall, and on the right, you have a rock avalanche. And the total risk from each of these scenarios is the same. They're both about 400 micromorts. But if you were to estimate risk only for events that happen up to the 300-year return period, you might find that the rock fall risk was 360 and the rock avalanche risk was 0. And that's because the rock avalanche is only low frequency, high consequence types of events. So just be aware that if you're estimating risk and you're only looking at the common events, you may be missing a very important piece of the total risk. So now I'll talk about the fifth lesson, and this is related to the risk tolerance. This is the second of those three factors that you're balancing in a risk evaluation. And the key message is that risk tolerance varies. There is no universal risk tolerance threshold. So I would have liked to have talked more about group risk. I just didn't have the time today, but what I'm showing on the screen is a very common tool that's used for group risk evaluations. It's an FN chart. So the y-axis here is the F. This is the probability of in or more fatalities per year. And the x-axis is the number of fatalities. So if you're making a group risk estimate, you would plot on this graph a curve that just shows the frequency of different numbers of fatality. And then you would compare that to one of these curves, which represent the risk tolerance. The reason I want to show this is that there are, each of these colored curves is a different threshold. So you should never assume that any one of these would apply at any particular place. The reason that there are so many different colored curves here is because each of these thresholds applies to a different type of hazard. It applies in a different political setting. It applies to a different scale of hazard. Some of these are for entire countries, whereas others are for individual sites. So just be aware that you can't just take a threshold from one place and apply it into another without understanding where it came from. Another reason that risk tolerance varies, and this could be varying even within a small region, is because the benefits of taking or tolerating the risk have a very large effect on the risk that is tolerated. So for example, if you remember my Guatemala City case study, the people living with the landslide risk, they're highly aware of the landslide risk, but to them that landslide risk is well worth taking because of the economic opportunity and educational opportunities and security that come from living near Guatemala City. There are large benefits, and that means we can take large risks. I also want to make the point, that's a related point, that if we set a very low risk tolerance threshold, so that's this purple line here of, let's say, 100, setting a low threshold that is unachievable can be counterproductive. And I saw this on a project I worked on a few years ago. So this project, it was a very high risk debris flow site, and it was a site that was scary, right? I went to this site and saw that, this is a place where we really need to do something because these people may be killed. So what we did is we estimated risk. We found that it was very high. We compared that to this threshold, and we wrote a grant application that said, look, the risk is much higher than the threshold. We need money to build mitigation. We received some money, but that money was a lot less than we had applied for. And then we came up with a design to reduce risk. And we found that the best we could do, being as efficient as possible, we could reduce that risk from 1,000 down to 200 with the money that was available. So we sent this design to the regulator, and we got this response. They said, we should not approve mitigation if it does not meet the threshold. Would a decision maker be viewed as holding public safety paramount if the project knowingly does not reduce risk to the threshold. So more money was not coming, and there was a moment when we thought that even this risk reduction was not going to occur because they weren't going to provide us the grant. And we've seen this happen in several cases where there's this mentality that comes in that kind of says, you know, it's better to do nothing at all if we can't go far enough to reduce risk. And this is all because of concerns about liability. Eventually, we realized that the problem was ours. The problem was in how we had framed the situation and how we had framed the risk reduction goal. So now what we do, and we found this to be much more productive, is to follow the advice of the U.S. Bureau of Reclamation. And instead of setting a threshold, we set a reference point, and then we talk about increasing and decreasing justification to reduce risk. And this allows us to do something like start with a risk way over here at 1,000 and take small incremental steps, common sense steps, to reduce risk until we get close to this line. And we've just found this to be a much better way to describe our objectives and to advocate for funding. We have found that a very strict threshold does apply in cases where two conditions exist, and that is a case where we have the resources to pay for very expensive mitigation, as well as a regulatory framework to enforce this strict risk tolerance criteria. And this, at least in the environment where I work, mostly with local governments, this seems to only apply when we have new development, and we're trying to decide if we could place new development within a recognized landslide hazard zone. So this brings us to the last lesson. This is related to the risk controls. And the lesson is that there are many ways to reduce risk. I come from a geology background. I would call myself a landslide person, as I assume many of you are as well. And when I think about risk, I also tend to focus on the landslides. And as I've done this more and more, I'm learning more and more that I need to stop focusing on the landslide and also think about the infrastructure that's impacted and the people that are exposed. So now when I start a new project, I try to think like a geologist and think about the landslide hazard, but I also try to think like a structural engineer who's concerned with the buildings and the infrastructure that's being impacted, as well as, say, a land use planner who's thinking more about land use planning and evacuation and site selection. And so we use this tool, this just simple tool, to brainstorm risk reduction options. We found it very helpful to put them into these three categories. After we have a list of potential risk controls, our next step is to identify the things that are constraining those risk controls. And those constraints can be things like budget, availability of land, political priorities, the technical feasibility of options, and then an important one is the ability to maintain a risk control in the future, because that's important for it to actually be functional. Another piece of information related to risk controls that's just critical to understand that you need to make space for is to understand the sacrifices that come with implementing the risk control. So, of course, there's the costs, there's the capital cost and the maintenance cost, those are obvious, but you need to also recognize the opportunity costs. So, for example, if you're a small government and you spend your money on a landslide risk reduction program, that money isn't available for other programs that could be more effective at reducing life loss risk from other hazards, or just bring more benefits to a community. So we've started to think a lot more about the business interruption sacrifices, the life experience sacrifices. So let's say you're managing a trail, there's a loss of visitor experience that happens if you close all the trails in your park. There's also the environmental impacts of mitigation and intangibles, like if you were to force the people in Guatemala City to leave these areas around Guatemala City, they're really sacrificing the economic security and educational opportunities that come with living there. So I'm out of time, and that's it. I hope that this very rapid overview I hope that you're able to take something small away from it. The highest level here, the key lessons that I hope you remember small pieces of are: number one is go slow and identify the decision that you need to make, and then set a path that's efficient for meeting that decision. This is the simplest mistake to make, and it's one that I've made over and over again in my career. The second lesson was that risk evaluation is complex, and we've tried to give some tools to help you gather the different pieces of information that you need to compare in the risk evaluation. The third lesson was to use common numbers that people are familiar with. I gave you the example of micromorts, but we have other common numbers that we use for group risk estimates that are described in the papers that I didn't have time to talk about. And then these last three, the number 4 here is, when you make a risk estimate, use a best estimate. Don't use conservatism, and also be careful not to underestimate risk by overlooking important scenarios. The fifth item here is to recognize that risk tolerance varies. It varies from site to site. It varies from person to person. And one large part of your decision-making process is to figure out specifically how the risk tolerance is perceived by the specific group of people who are affected. And then the last lesson here was to recognize that there are many ways to reduce risk that extend beyond reducing the landslide hazard. And then this is just an image that I want you to leave with in your mind, that risk evaluation is seeking a balance between these 3 different factors: factors related to the risk tolerance, factors relating to the risk level, and then factors relating to the risk controls that are available. Here's a publication list. I'm not going to go through these, but you can view the recording and then track these down if you want to. Or, of course, feel free to email me. I'd love to talk with you. Of course, everything I'm presenting here has been is not work that I'm doing on my own. I'm working with a large team of people, and these are just a few of the people who contributed to the work in this presentation. Thank you very much for your time, and thank you for this opportunity to present. That's all I have.